Hi class. I know you're having a great time at Tech It Out today, I hope, talking about how we created our database using database design techniques based on our Tech It Out registration. If you remember in class, we looked at this Tech It Out registration and our first step was creating a list of data elements. So we created a list of data elements like name, title, address, number of people. We went through the registration. We saw that there was additional information for sessions and notes for the order. And it's pretty basic registration information. So we made our list, and looking at our list of data elements, not super fancy yet, just scratched it out on the whiteboard, all of the different data elements that we're going to have to worry about and be considering. We took our list of data elements then and created some different entities that we felt like we needed to represent this information, like attendees, events, orders for the events. We have registration notes, sessions that are going to occur at a given event. Then we created a link table, a junction table for the intersection between attendees and sessions, because one attendee could attend many sessions and one session could have many attendees. So our link table will take care of that relationship for us. That's resolving that many-to-many relationship by creating two separate one-to-many relationships. So this is the database that we want to create. Of course, our next step would be to go to Visio and create a nice diagram documenting this information with all of our columns and rows. Everybody's done that already. So the next step would be to determine where we need to place indexes. Well, what is an index? Well, an index is a data structure that will be built by the database management system within our database files that will allow us to quickly retrieve data from our database, right? That's the whole point of having a database, is being able to randomly access a given row with specific information. So here's a picture of a clustered index, and a clustered index is one where the actual data rows are stored along with the index structure itself. So an index structure is going to be built on pages, and pages are simply pieces of our physical file. So when we create a file on disk or on a solid state drive, it's assigned a given block size or page size. That might be 40964K is a common page size. It might be 8K, it might be 16K, 32K. 32 kilobytes per page is also common. So this data structure is determined when the hard drive is actually formatted, and then the database management system just takes advantage of those existing blocks on the hard drive and refers to them as pages. So in this example, we have a few pages of our database allocated to an index structure. And this index structure can be considered a B tree or a binary tree type structure. At the topmost level of our index structure, or the root of the index, we have two entries. We say if the customer ID is between 1 and 10, go to page 1001. If the customer ID is 10 or above, go to page 1002 of the index structure. Now, when we branch off to this intermediate level page, we'll see again a division of data. If our customer ID is between 1 and 5, go to page 1005. If it's 5 or greater, go to page 1006. So here on page 1005, we see the actual leaf of our index. And because this is a clustered index, it also contains the data of our table, each row. So customer ID 1's row customer ID 2, 3, 4. Notice how our data is in sorted sequence already based on this customer ID key because we have a clustered index. So this clustered index is something that we want to use when we're talking about a primary key. It'll sort our data and save the data within the database in order so that we can easily access things. And as we're retrieving rows, if we're retrieving all of the rows from our customer table here, we're going to just start at this beginning page and get all of the data for page 1005. These 4 rows, our page pointer internally will point us to the next page. We'll continue gathering the customer rows, point to the next page, and we'll be able to gather all of our data within that customer ID sequence. Sometimes, well, back up here, our clustered index is automatically created on our primary key. So we don't have to do any sort of special commands when we create our database to create this clustered index. However, sometimes we might decide that our one clustered index for a table should be based on a different column, not the primary key. We only want to change that when the column is used in almost every search statement that we create for the table. The column contains mostly distinct values, like our primary key. The column is small, so it's kind of discouraged to create a clustered index on a very large column. We want to use a column whose values seldom change, and when most of the queries against the column will return a large result set. So in general, we don't want to change our primary key clustered index. We just want to let that happen. Database is going to take care of that for us. Now, we need to create some other indexes, though, on our own to enhance performance of our queries. Sometimes, for database design standards, we might like to put off creation of these non-clustered indexes until the database has been in use for a little while and we can determine where potential points are in the database design where adding an index would speed up processing. Let's think about this. Here is an example of a non-clustered index, and this index is built based on the name, the last name column. So if we were to be performing a query that ordered data by our customer last name, the database management system, when it determined what path to use to access our data, would automatically use this index. Its query plan would include this index. Now, why is that helpful? Well, say we want to find all of the people whose last names begin with the letter Z. We'd start at the beginning of our index structure at the root. Again, this index is built on pages in our database file. At our root, we would check and we would see that we want to find entries that are greater than Miller. So we would follow this path to page 2002. We want all of the Z's, so we would check this entry, this intermediate level index entry. We would see that we want entries greater than Stein, so we would follow the index pointers to page 2008. Again, we would follow that down and see that we want entries greater than Willow, so Willow is on page 1006. We would go then to our physical entries on page 1006 and start looking at every single entry to find all of the entries that had last names greater than Willow, or we would continue on our search and find the actual entries within our index structure that aren't shown here. We don't have any entries that have a Z. So let's try a different search. That wasn't a very good one. Bad example. Let's say we want to find our customer with the last name that begins with the letter L. As I check my index structure, I see that L is less than Miller, so I want to follow this first path to page 2001. Again, I want to find all the L's, so that's going to put me greater than hook. So I'll follow this to page 2006. Now I see that on this index entry page, I have levy that begins with an L. I can go find that data on page 1008 for levies row. And I have lows that begins with an L. That data is on page 1007 of our database. Here we go. Lows, page 1007, levy, page 1008. So that index entry will take us to that physical row where it's stored in our database file. The indexes then speed things up greatly. It's much faster than having to search through every customer row and go from the beginning to the end to be sure that we found all of the entries that start with the letter L. So we need indexes. We can have up to 249 non-clustered indexes on a table. The index is going to have to be updated when our affected data is updated. So if we change this last name Miller, we're going to have to update this index entry besides updating the actual data row. If we add a new customer row whose last name is like Noel, we'll have to insert that entry, so that may cause updates to multiple pages of our index. So our index does have some overhead associated with it. Sometimes we need to build an index that's a composite, that's more than one column. For example, if we have a link table where we want both key columns to be indexed. Sometimes we have a query that's very specific and runs often. We might need to create an index just especially for that given query, and that's called a covering index, an index that's built just to help one query or many queries in our company. Now, if we want to see if our query is being properly used or our index is being properly used by a given query, we can use the query tool in SQL Server Manager and display the estimated execution plan to see if an index should be added or make sure that it's being used. Now, when do we want to create an index? Usually on foreign key columns, on a column that's used frequently in a query or a join, a column that contains a large number of distinct values, and a column that's updated infrequently. Now, sometimes we have to create an index on a frequently updated column, and that does cost us some overhead. Now, here's an example of how we might want to look at the data in our database. We might just do a table scan, and a table scan would be where we just go to the page in the database where our data rows begin being stored, and we just scan every single one looking for information. You can see that that can be a pretty expensive type of database access, so that's why indexes are important. Now, we don't have a specific tool to document the indexes that we create. We could add that information in a list, or we can assume that we're going to have some indexes on all of our foreign keys. It would be nice for us to have a list on our Visio diagram of what indexes we need to create. You and your partner, I know, have created a Visio diagram. I'm going to bypass that step, at least in our presentation here, so that we don't use quite all of that time. So we're ready to create our database. We're going to use SQL Statements, a special type of SQL called DDL, Data Definition Language. So we've seen so far that we have queries, DML, which is Data Manipulation Language Statements, and DDL, Data Definition Language Statements. So we're going to look at these Data Definition Language Statements to see how we create tables. Just like when we're updating data, we have very specific keywords in SQL, we have insert, update, and delete to modify the data within our database. We have specific keywords to create entities, objects within our database or the database itself. And those keywords are create, alter, and drop. So we want to make sure that we don't get those confused with the keywords that we use to change the data inside the tables. So if I wanted to insert a row, I would use insert. If I want to create a table, I would use create table. So each of these keywords uses very specific syntax. So when we think about it, it's very simple. Our first word in our statement is going to be the keyword, the action, create, alter, or drop. The second word is going to be the type of entity we're referring to. So I want to create a table, or alter a table, or drop a table. So if I'm working with an index, I would be either creating an index, altering an index, or dropping an index. Now, as we look at these basic actions that we can do to define database objects, notice the different types of entities: database, table, index. We've heard of those things. Function, we've heard of. But the functions we've heard of so far have been functions that exist within the system. These are functions that we create ourselves. We also have a sequence object, a procedure, a trigger, and a view. So a few more things for us to learn here at the last end of the semester. So for each of these object types, we can create them, we can alter them, or we can drop them. So how do we name objects with the database? Basically, we decided that they were pretty much the same naming standards as we're used to with programming, but we have a little bit different rules. So we have the first character has to be a letter, an underscore, an @ sign, or a number sign, or a hashtag. All characters after the first letter must be a letter, an @ sign, a $sign, a number sign, or an underscore. So notice that we add the $sign there. We can't use a reserved word like table. An identifier can't contain spaces or special characters except for those ones that we've mentioned. So here are some valid identifiers. Remember, when we put square brackets around a name, it becomes a delimited identifier, and we can get away with things like spaces. We can also use double quotes around a name to make it a delimited identifier. Notice with the % increase, we were able to get away with using that special character because we have delimited that identifier. So let's look at our create statement. If we want to create a database, we're going to use the syntax create database followed by the database name. We have some optional keywords, but that's all we have to have. Create database, new AP. Now, the optional keywords will let us say what specific file we want to use in our file system. So that's some more advanced things. But we can really get down in there and control how this database is allocated in our file system. Now, when we're talking about creating databases, in our environment, we're limited to the number of databases that we can have on our Amazon web server. So your user database is the only database that you'll have access to. So we won't be creating additional databases for this group project. So you won't have an opportunity to issue the create database command. But that's okay, because you can see it's pretty basic syntax. Now, because we won't be able to create an additional database for your group project, we're going to prefix all of our table names with the letter G and a dash. So we'll have G underscore, and then our table name, not a dash, underscore. So when we do our create table statements, we're going to create all of the different tables that we need for our database, and we're going to put a G underscore in front of them so that when you look at all of the tables that are within your user database, you'll know which tables are part of your group project. Now the syntax to create a table again is create table and then the table name, but tables don't mean anything unless they have columns. So our create table syntax is a little bit more complicated because we're going to follow the table name with a list of our columns. For each column, we're going to specify the name of the column, its data type, and any attributes of the column. Now our attributes are those ones that we've seen in the GUI create table specifier, null and not null, if we want something to be a primary key or unique values, an identity column where we want the database to automatically assign a value to our column. If we create an identity column, we can specify the beginning and ending, or the beginning value. We also could specify a default value for this column, and sparse. Sparse meaning we don't want to save things unless absolutely necessary. Now here's our syntax to create a table, our vendors table. So we're starting out saying we're going to have the vendor ID, it's an integer, and we want the vendor name column, and it's going to be a variable number of characters of up to 50. Our column list is enclosed within a set of parentheses and followed by a semicolon. The next syntax example shows a create table statement for our invoices table. We have our invoice ID that's an integer. It is our primary key and it's an identity type data. So that means SQL Server is automatically going to assign a unique value to the invoice ID column for every invoice row that's created. We also have the vendor ID column on our invoice table, and it cannot be null because an invoice cannot exist unless we know its vendor. We have our invoice date, and we're going to use the small date time data type. We are okay with nulls, and we're going to use our invoice total column is going to be a money data type. Nulls are okay, but the default is 0. Sparse tells, again, the database to not save this data if there's no value. So if there's a no value, we won't be wasting space on this address too, because we may not have it. It's sparsely populated. So that takes care of our tables. Next, we need to create indexes. Most of our indexes, as you know, are non-clustered, so that's the default. If we say create index without specifying clustered or non-clustered, it will be a non-clustered. We're going to give our index a name that normally starts with IX underscore to indicate that it's an index within our database. Now the next keyword for our create index statement is the on keyword. The on keyword is going to specify what table this index applies to, and then within parentheses the columns of that table that this index should be built on. So here we're creating an index on our vendor ID. So for our invoices table, we want that vendor ID index because vendor ID is a foreign key for our invoices. The next example creates a non-clustered index for us on our invoice date and invoice total, because this is something that we feel like we do a lot of queries on. Okay, so remember again, we're going to get that clustered index saved automatically for us. Now we can also create a filtered index. This is an index built on specific rows that meet data requirements. Here we're creating an index on the invoice payment, and we're calling it a filtered index. good to put that in the name so that we're aware of that when we look at it. This index is created for the invoices table on the invoice date in descending and invoice total. But we only want those invoices that have not been paid yet, where our payment date is null. So this index will be very dynamic and only contain our unpaid invoices. Here's another one where we create an invoices date filter on that invoice date and invoice total for dates greater than a certain time. So we can do this to create indexes to speed up queries. The Snippet Picker is a special tool that's within the graphical user interface of the SQL Server Management Studio. We saw that we could create a table using the GUI. We could also insert a snippet. You go to the Snippet Manager and click on Table and choose Create Table, and the Snippet Manager will insert this syntax for you. Create table, sample table, with our opening and closing parentheses and some sample columns. So if we can't remember the syntax, we can use that snippet tool. Okay, so far we've seen a few things that we should clarify. We saw the filtered index. Now, all other types of indexes are full table indexes by default. We saw that when you created a database, you could attach a database file, and another option in that created database was the transaction log file, which is a log of all of the activity that occurs within the database. So we can control where those files are allocated and created on our file system, because our database is very busy. Now, we were talking about columns. When we create a column in a table, we had column level options. We saw not null and primary key, but there are additional constraints or rules that are available. Constraints are the fences that we place around our fields so that we make sure that the data in the field is valid. A unique constraint says that this value must be unique within all occurrences of our table. So this is the only time I can have that value. A check constraint is one that sets up limits on values, like the amount due must be between 500 and 1,000. That would be a check constraint. A foreign key constraint is one that we can create within a relationship that says that we must have a vendor in our vendor table that matches this key before we can insert an invoice. References is a keyword that creates that relationship between the two tables. Now, at the same constraint idea, we can have constraints that apply to our table. We know already that our primary key constraint says that that column must be unique within our table. The check constraint limits the values for one or more columns in the table. We can apply a foreign key and a references statement to enforce referential integrity between one or more columns. So let's take a look at that. Here we're creating our invoice line items table. We've added a 1 here. You can try this syntax. We're creating this table on the invoice ID as an integer. We do not allow it to be null. An invoice sequence column that's a small integer that cannot be null. And our line item amount that's a money that cannot be null. Our primary key here is going to be our invoice ID and our invoice sequence. So we have a composite key. In this example, when we create our table, we're mentioning that our invoice total must be greater than or equal to 0, can't be negative. Our payment total must be greater than or equal to 0. Those are check constraints on the column level. Now we could create the same check constraints at the table level totally just a matter of how you want to do it. We can say that on the invoices table, we have this check constraint that the invoice total must be greater than or equal to 0 and the payment total must be greater than or equal to 0. So again, you could do it either way. So the syntax for a check constraint is just the keyword check followed by the condition within parentheses. When we've created a check constraint, we could see an insert statement fail because the check constraint was violated. So we'll get something like this. Check constraint conflict occurred. We cannot insert that invoice because of the invoice total column. So we can enforce that integrity. Now here's a more involved table level check constraint. We're saying the vendor code has to be like this whole key, right? And we're saying that column 1 must be an uppercase letter. The next column must be an uppercase letter. Next we have a number, a number, a number, and a number. So we're using pattern matching to specify the format of that vendor code. And the vendor code's leftmost 2 digits must be the same as the vendor name's leftmost 2 digits. So we would fail here because of the way that's set up. So we can enforce all sorts of check constraints. Now we also need to add foreign keys. So we can add a foreign key constraint by using the keyword foreign key. When we use the keyword foreign key, we can specify references. Note that out of this syntax, the references keyword is the one that's required. So the foreign key keyword is optional. It's in those square brackets. References is not optional. So we say references, this other table, and this column of that table. And then we add in what kind of additional rules we want to create for this foreign key constraint. Do we want to cascade deletes? Meaning if we delete the vendor, we want to delete all of the invoices for that vendor. Do we cascade updates? Meaning if we update information on the vendor row, that affects the invoices should they all be updated automatically. So we can cascade those kinds of actions if we like with this relationship. When we are creating our foreign key relationship at the table level, then we do require the foreign key keyword. And we're going to specify what columns for this table that we are creating are part of this relationship. And then we're going to add the references keyword to say that it references another table and those columns. And again, how we want those updates and deletes to be handled. Here we're creating table vendor. It has vendor ID and vendor name. And then when we create our associated invoices table, we're up to 9 here. We create our invoice ID as our primary key. Our vendor ID, which is our foreign key, we say this references this other table's vendor ID column. So now we've created that relationship between those vendor IDs. So when we do join syntax in our select statements and we say join invoices on vendor.vendor ID equal invoices.vendor ID, the database management system knows that there's a relationship there, and we have that index built, or we will, to create an easy query. Now, if we violate our foreign key constraint and we try to insert an invoice with a non-existent vendor, we'll get an error and we won't be able to do that insert. So constraints are those rules that apply to columns that keep our data valid, our field level fencing. Our column level constraints apply to a specific column. Table level constraints are applied at the table level and might impact multiple columns. Check constraints are checking to make sure that we are receiving valid values. Foreign key constraints are verifying that data exists in related tables. Reference constraints, like a foreign key constraint, allows us to make sure that a relationship can be enforced. We can cascade deletes or updates through those relationships. Now, if we've created an index and then we don't want it anymore, we can drop it. When we drop an index, we're going to specify the index name and use the on keyword to specify the table. We can't delete an index that's based on a primary key or unique key. To do that, we'd have to use the alter table statement. We can drop a table, and oftentimes if we try to modify a table, we'll find that we're not able to. We have to actually drop the table and then create it again. It can be a problem. We can't delete a table if a foreign key constraint in another table refers to that table. So we have to make sure that we create and drop things in the right order. When you delete a table, all of the data, indexes, triggers, and constraints are deleted. Excuse me. Any views or stored procedures are also deleted. We can drop our database with the drop database command. Get rid of the whole thing. Now, what we want to alter things without dropping. Yeah, we can try, but often it's hard to alter things once there's data within your table. So let's see what we can do. The alter table statement is kind of complex. This is another reason people often drop and then recreate tables. When we're altering a table, we could add new columns, drop columns, or alter existing columns. We could add constraints or drop constraints. As you can see, it can get kind of messy very quickly. If we want to add a new column, we can do so easily enough. Alter table, add column. If we want to drop a column, again, pretty simple syntax. Add a new check constraint, add a foreign key constraint. Changing the data type of a column could give us a little bit more trouble. Here we're using the alter column syntax and saying we want to make this a variable character size of up to 200. So the database management system will let us do that if our current data type can be easily transferred to this data type. But if our current data type were going to have to be truncated to fit in this 200, we would get an error. Okay, what is a sequence? A sequence is an entity that exists within our database that gives us a unique value. So we might have a sequence where we are offering up to all of our convenient fuel locations across the country what the next available invoice number is. So we can't create this invoice number as an identity column within a table because our database system is too complex. Instead, we have a unique value that is accessed by a service, a web service, that is the next available invoice number. So every time one of our fuel locations needs an invoice number, that web service that we've created will access the sequence within our database and update it. So this is really cool. We'll try it in class. We can all work with the same sequence. So we create a sequence within the database. We set a starting value. We can also set an increment. We can set a minimum and a maximum, and we can set up a cycle amount, like how often things start over. We can create a table that has a sequence column, and then we can keep track of that just like it was an identity column. This syntax will allow us to get the current value from the sequence test sequence 3. So we can use a select statement to get the next value. And then we could drop that sequence from our database or alter it. Now, often when we're working with a database, we want to create a script. And we've been creating scripts when we save the SQL code that we create in SQL Server Manager. But we've been creating like a select statement, maybe a couple of statements. When we're working with creating database objects, we can have a much more substantial script because we can have all of our create table syntax, all of our create index syntax, everything all in one file. And that's what we need to do. So as a database manager, of course, we're going to have the script file saved somewhere to be able to recreate all of the tables and entities within our database in case something were to happen or we needed to recreate the environment for testing. So we're going to have this entire script of every piece. Now we have to create things. Now each of those items that we put in our script can be considered a batch, and a batch occurs every time we have a go statement. So we've been doing that on our own when we create our SQL statements, saying that we want to use a specific database, following it with a go. That's a batch. And so every time we run into a go statement, we will have a batch. So I want to create some new tables. Just thinking here about it. So I'm going to use the new query window. Before I do that, let's take a look at our AP database. From the AP database, I can actually right-click on the database itself and say script database as create, and I want to send this script to a new query editor window. This database already exists, so I can easily generate the create script for this database. So you see it here, it does the create database statement. It does some alter statements based on some things that the system decides we need, and then creates the database. So we would have to generate a script for each table within our database to get this entire script generated for everything. That's why we want to do it as a database administrator. We're going to keep track of this information and have our own script. All right, so I'm going to do this within my database. So I'll close this window and, oops, where am I? Let me create a new query window. Here I am. So I want to use my database. And the first thing that I want to do is figure out what table to create first. Can I just jump in there and carry create tables? Well, I could, because right at this point, when I first create tables, I don't really have any relationships created or anything like that. But if I look at my design, I want to kind of figure out what are my primary tables, what are my anchor tables. Well, one is my event, right? For one event, I'm going to have many orders and many sessions. So my event could be considered an anchor table to these other tables, or even a parent, in effect. Then my attendees table is also an anchor for an order. So before I could insert an order in the database, I would have to have an attendee for that order, an event for that order. So that means my order table really shouldn't be created until after I've created the event and the attendees. So we want to take a look at those kinds of things to decide what order we want to create our entities. So I think I would want to create an event first. That is an anchor for me. So I would have create. I want to create a table, right? Now, I want to look at the syntax here. And according to the presentation that they give, they always make the entity type all in uppercase. along with the keyword. So I will make it be in uppercase. And then that will key that that's my required syntax. This is part of my group database. So I'm going to put G underscore in front of my table name. And I want to create my event table. Now my event table had some columns. So I can go ahead and put those parentheses in there for my column list. Let's take a look at what we want there. For our syntax, we're going to have our column name followed by the data type. Now, what columns do we need for our event? I've got to go back to my data list because I don't have a very good diagram created. Our event had event title, the location of the event, which we decided should have multiple fields to be simplified. Address 1, address 2, city, state, and zip. Our event date and time. Okay, so I'm going to move this out of my way a little bit over here. If it will go, there we go. So in our event, we want an event ID, right? Now our event ID is going to be an integer. We're not going to allow nulls. So just like this one, we want it to be an integer that's a primary key, that's an identity column. Does that look right? Looks good. Now, after our event ID, then, we need our event title. We'll make this a variable number of characters of, let's say, 100. I'm going to go up and tab this over a little more so we can keep things in sync. Now, for our title, because our event is so important and the title is important, let's say that cannot be null. Next, we want our address information. Address 1. Address 2. And our address 2 is going to be sparse. City. State. Looks like state is a keyword, huh? So we can't use that. We'll just make it ST. And zip. Just gonna go 20. All right, so that's our address. Now the other things that we had for our event were the event date and time. I think that we want our location name. Make that a little shorter. And then this is all going to be our location information, address, all that. So let's put our event date and time right under our title. They use small date time. That looks good. We'll try it. And looks like I need to make all of these uppercase. Ooh. Okay. But you don't like that. All right, so after our date time, is there anything that we want to specify about that one? We're okay with null. We'll do that for all of our rows. We're okay with null. Sparse has to come first, of course. So that takes care of our event table. Now our event table is, as we mentioned, kind of an anchor table, so it doesn't really have any dependencies on any other tables. In order to create a script where we could continuously run the script over and over, we could go ahead and put a drop table statement here for our event table and make that a batch, and then we could create our new table as we want. Now it's complaining at us because that drop saying, hey, you know, you don't really have this table created yet, so I don't know how you can say you're ready to drop it. I think there's something we can do about that. Hang on, let me get this file open. I'll just leave that there commented out to remind you that you want to be able to drop that table and recreate it. Let's go ahead and run this and see if it works properly. It says it ran just fine. If I refresh my table view, I should see my new G_event table. So everything is good to go. Now I know you're going to have to do some experimenting with the syntax. Remember, you want to create things in a certain order. After I create my event table, I would want to create my attendees table. And then as I go, I could create my order table. And as I create the order table, I can create those relationships between the order attendee and the order and the event. Your table, I know, is a little different because you're working with the Dr. Bill, so you'll have some different entities and some different relationships. After you've created tables, You can create indexes, specify those. You can put some check constraints into your database. I would like to see at least one check constraint. There needs to be an index created on every foreign key in your database. As you create these entities, don't forget the G_table names will keep these separated as your group tables within your database. I would recommend that as you create your script, you include drop syntax and you think about the order that you're going to have to drop things as compared to the order that you created things. It's kind of a backwards drop. So I would create the event table first. That means it's going to be the last thing that I'll drop. So I would create my event table, create my attendees table, create my order table that's dependent upon both of them. Then if I wanted to drop things, I would drop those relationships, drop the order table, drop the attendees table, then finally I could drop the events table. So experiment with it with your partner as you're creating and working on your database. Hope you had a great time at Check It Out and that you see how simple it is to use these commands. The hard part is figuring out the logical order in doing so. Thank you.